Okay, everyone. Nice, Nick Farr. He just ran downstairs, so please let him get some air first.
Okay, check, check. Hello? All right, good evening, everybody. I'm glad to see that this is a packed room. I'm really sorry I'm late, but they wrapped me in this. I'm actually not kidding. At the worst possible time. I think all of maybe... Well, I kind of whispered in Honk's ear like it's time to stop making sex jokes in Saw 1 and time to get me because I actually have to be on stage somewhere else. And he was like, oh, I'm sorry, we didn't know that, I'm sorry. And so him and Bug Blue pick me up off the stage and then carry me off, rip it off, and then I come running down here. Don't give them any ideas like that. Okay. I really hope it's not. But it probably is already on YouTube. Okay, anyway, thank you. I just wanted to thank, again, Hackspace for being so awesome. I know I'm wearing a Ramzite Labor lab coat. Can we get a round of applause for these guys? Seriously.
Thank you.
I'm very honored to be here and to give this talk. This is exactly what we were talking about at the camp. And I'm glad to see that Hackspace has taken the ball, picked it up, and started running with it. Because, as I was trying to explain at the camp, today's networks are evil. They're based on old technology. This is exactly the kind of thing I was saying. We should... What?
You're one behind.
I'm one behind?
That's the next one. That's the current one.
Okay. Sorry, I apologize. And I was just saying, why don't we have connections everywhere? Why is it so difficult to get connected? Why are people who live in rural areas or people who aren't, in heavily urban areas have really fast connectivity just because they don't live in the right place? Why is the old technology not allowing us to have better? Why is the old technology not allowing us to have absolutely unlimited internet everywhere that's fast, that's high quality, at a very affordable price? Why is the connection technologies that we use today based on old business models? I personally don't think that makes any sense. And I'm an accountant. I mean, the networks today, they're not open. They're proprietary, they're old-fashioned, and they're insecure. I mean, that's what we spend most of our time talking about at these conferences. But, Okay, when you're supposed to give an important talk, do not let the people who are your friends wrap you in saran wrap. Okay. All right. Okay, I should probably look there. But things are changing for the better. I believe that there is this better solution out there. But, like I was saying at that camp, we're going to have to do it. Because it's not going to be the people that are providing these services today that are going to bring us into the future. I mean, the kinds of people that build systems that help us explore the moon and don't go back for 40 years cannot give us the network technologies that we know are possible, that everybody in here, I believe, knows are absolutely possible. We're going to have to do it ourselves, right here. Everybody who attends these congresses and hacker conferences all over the world. We know science. We do science. A lot of companies do science, but they do it not for the love and for the passion of it like we do it, but they do it for profitable purposes. Building the networks of tomorrow are going to have to happen in this community. We're all going to have to get to work doing it. And at the same time, I believe this community is also much more flat and much more transparent than the communities that are currently providing our network services. Not only are we the people who are designing a lot of these systems, but we're also users, and we're much more well acquainted with the user base. We also believe everybody should benefit. Open source technology, all of these open source operatings, free software, free everything, free culture, Creative Commons, all of those sorts of things are powered by communities like ours. We believe everything that we create, everybody should benefit from. And we're very good at distributed networks. There's a lot of well-established distributed networks that I believe this community has had a very big role in building, creating, and using every day. IRC is a perfect example of this. You know, that's how we connect a lot of these talks with people who are watching the streams at home through IRC, and a lot of us use IRC every day. Skype, example, it's evil, but it's a distributed network. Tor, another perfect example for trying to protect our privacy, trying to protect rights that a lot of these people that are providing these services are trying to take away from us very, very incrementally for profit or for political purposes. SETI at home is another perfect example of a distributed network for science. Freifunk, OLSR, that's something that this community directly has a hand. Can I just get a round of applause for those guys, that people are trying to provide free Wi-Fi. Because distributed mesh networks are hard. And of course, peer-to-peer networks like BitTorrent and importantly, Bitcoin, you know, making money, the transfer of value, that's something that this community through Bitcoin has done really well, has been experimented with, and is actually put into practice and made use. Basically, all of these technologies, things that we're developing, what do we want? World domination, right? Am I right? Right? And we can do that through information. And we're doing that every day through sharing information and making fast, cheap, secure. I didn't do that intentionally, I apologize. Fast, cheap, secure, and reliable ways of making network connections accessible. That much is not a joke. That's something that we're working on and that we're doing every day. And even those of you, I know a lot of people at conferences like these will approach me and say, you know, I don't really feel like a hacker. I don't do certain things. No, that's all of those excuses, and I've been saying this for years, all of those excuses are invalid. Every single person in this room, no matter what you assess your technical capabilities as, can help, can join, can make a difference. Doing it very, very easily today. It all starts with a very simple, small device, right here. No, bring it up, hold it. Yep. And these guys are going to tell you all about it. Thank you guys so much for letting me open this up. This project means very, very much to me, and I hope after this presentation it'll mean a lot to you. Give these guys a huge round of applause for making the first step. The first step in what will be a giant leap for hackers and a giant leap for mankind. Thank you very much.
Thank you, Nick Parr.
Thanks.
Thank you, Nick. We decided when Nick called upon us that there is a need for space and communications in space. There were 3 hackers sitting on an express train to Berlin, and we've had a giant brain fart. We put ourselves to the task and decided upon our goals for the next few months, and that would be understanding, building, owning, and all that open sourcing a distributed ground station network. Of course, there's a couple of short-term tasks ahead of us, which are, first of all, receive some signals, then decode the signals, understand what's in there, and then finally record and store them for later data processing. So there is a long way ahead of us, and we've identified a couple of things that we need to understand first. Satellite communication protocols, I bet there are a few. I don't know any yet. There's lots of high frequency and antenna stuff, analog and digital filters, all kinds of electronics and nastiness, also including mathematics and cryptography, that we still have to learn a lot about. So how do you get started? It's a really, really big project, and There's one article, though not hardware related, but software centered, I would really like to recommend all of you reading if you're working on anything that's bigger than one page of code. It's a really awesome article by Jeff Wofford on how to not get stuck. And the basic idea is break it down into as small packets that you can work on as possible. And as I said before, knowledge is purely optional because I can tell from my own experience, I don't know anything about HF or antennas. I built them anyway. So what do we want a ground station for? We want to do everything. And I have to admit that eierlegende Wollmilchsau sounds a lot more awesome than a all-purpose device. And that will not work. So we will work on something that is more like Unix and Power Rangers. Many, many small things that you can combine to something big and awesome. So what's the most basic thing that we need in a distributed system that we want? It's timing and synchronization, because there's no point at all measuring anything if you don't know the exact time that something had happened. So we need high accuracy. Let's arbitrarily select better than a microsecond. An easy-to-use interface, because we want to have anything exchangeable, because, well, we will make errors and failures along the way, and we just want to unplug something and replace it with something better along the way. Then, well, it has to be bigger and better over time, and yeah. Okay, time source it is, and we've identified 3 candidates, and Relocate will take over from here.
So, 3 candidates, NTP, DCF77, and GPS. And about NTP, we can say it's too simple and requires a permanent internet connection. And so we said, skip that. And we went to DCF77, which is the thing we know in Germany as Funkuhr. And it looked like a very simple task with this protocol, because you get 59 bits per minute, and with every coming bit you should know exactly now the second starts. And this seems like a good thing for synchronization, but it works only in Central Europe. On other continents there is other systems that work similar, but they are not synchronized to a central clock source. And there's also things with that the receivers you can buy are usually very sensitive to touching people being around them. They just tend to stop working after a while and then start again. It was a great mess. So we decided to use GPS, because there's existing hardware to do it. It's possible to use it almost everywhere. And since we also need to know where we are, we can use it for this purpose too, so we would have needed it anyway. And some GPS modules, I think even most of them, have a super accurate pulse per second pin that goes up once a second. The problem with GPS is that it's not independent from current Earth politics, and if current Earth politics allowed it to be, it would be more accurate and more cool. And it's also very high frequency stuff with very strange physics, and yeah. So we decided to try it out with something we knew that would work. Just plug it together and see what it does. We used an Arduino Mega for this, which has 4 hardware serial ports that can not only be used to communicate with the GPS module, but also with a computer or other microcontrollers in the ground station.
Without interfering with timing at the same time, because
Yes.
that was a problem we had with the Duo Milanova Arduino.
That's right. And our first results looked very promising. You can see here that the lower signal flips every second. Laser pointer. Yeah. Yeah. Every time the signal changes, a second has passed, and you can see it's. What? I can't find it, but it's. It happens after 1 second.
It is actually triggering a monoflop, which explains why the frequency is 500 millihertz and the period is 2 seconds.
Yes.
Because the pulse you get from a GPS receiver is very, very small, and you wouldn't actually see it at this scale.
Yeah. So we know from the GPS module when the second starts, and the rest of the information, like which minute, which second, we can get by reading the NMEA information over the serial connection with the awesome hardware UART. So, but there's more. We have here a picture of 2 GPS modules running in parallel. They lie next to each other, so they're probably connected to the same satellites, most likely. And the oscilloscope was triggering on the first one. And as we can see, the timings do differ a bit, but it's about 200 nanoseconds, and that's less than 1 microsecond, and so it's good. Yeah. Okay, we have currently we have a 16 megahertz clock driving the microcontroller, and then we can try to interpolate stuff, and that means we have a working time source so far. So the next step is a bit of design of the in the design of the station, of the ground station. We have to define a timing module because we want everything interchangeable. We need an accurate time source to do this. We need a higher frequency clock to increase the resolution of the module and to keep track of the time. And we have to interface it with I2C or I2C or an interrupt or something. We'll see about that. And the next step would be defining a positioning module that tells us the position where our ground station is. And also there are many possible things. You can use GPS, we can use GLONASS, we can use hard-coded coordinates because we have measured where the ground station stands and it's fixed there, or we can use the very new Galileo that was launched a few days ago. First launch.
It was activated some days ago. It was activated some days ago.
So, and this leads us to a ground station with these 3 modules. And I give back to Hades.
So now we've got timing and positions. So what do we actually want to measure? Satellites at this point are a little difficult because we don't have any, but there's plenty of airplanes flying around over our heads. And each of those is sending a signal called ADS-B, which is just a beacon signal every commercial airliner is sending out. And it includes, besides the call sign, flight number, also the GPS position and time of each plane. Of course, there's a couple of cons there as well, because it is a signal sent at roughly gigahertz, and that is SHF, which in German is scheiß hohe Frequenz. And scheiß hohe Frequenz is really nasty, but that makes it also really awesome. Now, well, introducing the ham radio community, and I'm sure there are a few in here. Who is a ham radio operator? You guys are awesome. But, yes, a round of applause for all the ham radio operators. You do awesome stuff, and some of the documentation we found is really, really obscure. Here's some feedback. We had to build an antenna, and we decided, let's build a J-pole or a Slim Jim in the next iteration. That's the documentation we found. How to build a J-pole antenna. It was make this part here 22 centimeters, this one 6.5, and make this a centimeter or something, and then start nibbling off 2 parts here and 1 part there to tune it, and that is really obscure. I didn't learn anything from that. So we had to spend some time reading more documentation, and then we found this. It's actually here, that's 3/4 of a wavelength, and that's 1/4 of a wavelength, and then you have to adjust this little bit here to get the impedance down here to 50 ohms to match your cables, and that's how you actually learn something from it. So we've learned that you shouldn't document what you did, but how you did it, because only that way we can all learn from each other, and that is the main task here. So it is work, and many hackers document their stuff similar to this, and I just kindly want to ask, get better at documenting your stuff. You could also build a Slim Jim antenna, which is similar to the J-pole in design, kinda, and it got a little more gain and some other details which you can read about in the linked references in the end somewhere. Okay, we've got an antenna, and now we need to receive stuff. So we found actually that same ham radio operator that we got the weird documentation from, and he used old satellite TV tuners to receive ADS-B and decode it. We started doing that, and then noticed he's actually exploiting a hardware bug. It looked so good when we started. It wasn't. Anyway, we bought shit and got it working. This is a mini ADS-B module. It is kind of open. You can buy a kit, solder it. It's nice SMT components. I like that stuff.
And even works in the BCC.
Yes, and it even works in the BCC. You can come up to our desk and take a look at it.
Yeah.
And that's what it looks like. That's an airplane, if you can't tell. Anyway, we've got a signal. Now we need to do some more filtering and amplification, because the signal we get from the decoder is a little bit small. It's 0.1 to 0.3 volts, and that is not that much. Anyway, then we do some decoding measurement, and then we notice, oh shit, it's the 28th. Anyway, that's where we are at, and we actually get a lot out of this project, even along the way. So what do we get? We've got a distributed timing network that we can use to measure anything we want. You can measure your weather stations, airplanes, radiation, earthquakes. It really doesn't matter if you're measuring satellites or whatever. And we have plenty of GPS ground stations, if everything works out, that actually know their location. So we can do AGPS, which is assisted GPS, which makes it even more accurate for all kinds of other applications, because we know the position of the ground station and what the GPS thinks the position is. And we've got distributed time sources, which, well, everyone needs time. Next up, we actually have a second ADSB receiver that we need to get working. Then we have to set up those two receivers a couple of miles apart, measure some signals, and calculate numbers. Then, if we don't get crazy on the way because it's so much high-frequency stuff, we'll try harder and build more, and there will probably be many, many dragons. And so far, there's been quite some collateral damage. We got lots of contacts into the ham radio community and the satellite community. We've built 3 antennas so far, despite our utter lack of knowledge. We've got 2 ADSB receivers, as said before. We've got several GPS setups and many, many filters, some of which don't actually filter. Then we've got a GPS module that is made specifically for timing that we're going to take a look at. We've got one hacker lost in the lands of FPGA design because we need higher clock rates. And we've got one hacker lost to horology, which is the art of measuring time. He actually found a really nice paper, 100 pages. Yeah, tons of fun. Anyway, it's too much for us to do, and there's this little stuff that we got. The first try of getting anything to work. Lots of receivers and crap. It's fun to take that stuff apart. Anyway, how to contribute? You can do the usual stuff. Write code, talk to us, help us, share your expertise if you have any. I'm sure you have. And finally, if everything works out, set up a ground station. And we actually do have one guy here that has an application for all of this already. Andreas.
Okay, now it's my turn. Like presented before, you know how to do it with hardware, but you want to have it distributed. So I will tell this later. So what the fuck are we doing here right now? So we want to build a real space application. So we want to have telemetry and tracking, and with a real purpose. For my University of Stuttgart, there's a small satellite project at the IRS. That's the Institute of Space Systems, and they want to build a small satellite, and we want to track and do telemetry with it when it's done in orbit. And we want to determine the orbital elements, that's called Keplerian elements, that define the orbit. And we want to have the amateur radio community included in this all. And we want to have it externally tracking and positioning, because it has some benefits with it. So why do we want to do it? So why not? So first of all, it's positioning. When the satellite is ejected into the orbit, sometimes you don't really know where the launcher is heading you to. So you're bored in orbit, and sometimes you're not there. And you want to know where the launcher put you to. So relatively fast after the positioning of orbit injection, you want to have the positioning. So like you can see here before on the slide, when there are so small variants inside, you're not aiming with your dish directly to the satellites, and so you don't get any connections at all. And we want to have it globally, and we want to have an independent service. Then afterwards, when the tracking is possible, we want to have also some kind of communication with the satellites. In this case, it's a so-called data dump mode. We want to get signals from the satellite, like some housekeeping data, the temperatures inside, and some other really important data that will be sent down. Then our distributed ground station network over there could fill in some gaps between the main nodes the satellite owner already rented, so you can fill some gaps over there. And in the very, very last end of it, we want to have a possibility to command satellites. Okay, that's a really, really high expectation here. And there's almost nothing more important than data rates in space, so you could help us doing this and achieving it to be somehow a little bit cheaper then. And the last thing is, of course, to serve man in general, to have the telemetry and tracking of satellites for everybody, some derivatives beyond this current objectives, of course, and a science platform. And that's a picture how it's done currently. So there's big satellite dish on some fields. That's a Rasting Satellite Earth Station, and we want to have something like this. That's that's somewhere nearby in building like Köln, and everybody should contribute, like not perhaps with this television satellite dishes, but with some other kind of antennas these guys are building right now. So how do we start? First of all, we need 4 dots, and these dots are reception stations. And we want to have some kind of reverse GPS, so you need to have at least 4 GPS satellites and a handheld device. And with 4 GPS satellites sending signals to your handheld device can calculate where it is. So we want to have it backwards. Your handheld device will send out something to the antenna, to the reception station, and then we will calculate it backwards. And this is done via pseudo-ranging, it's so called, and we have to have at least 4 stations because it's in 3D. And this is, it's easy somehow, but it's solving lots of linear equations with matrices. So that is nothing new. So the so-called Apollonius of Perga did this some 1,000 years ago, and his finding is already available in the internet. And there are some other papers describing how it will be done. So it won't end with 4 dots. We need to have U at some point, because you want to have more reception stations distributed all over the world. Because then we can enhance the accuracy of everything through multi-reception points, and then it will become a combinatorial problem with some exponential deterministic behavior. So the more stations you got, the more the computer has to calculate afterwards, but like shown here, your position accuracy will be much, much better, or at least we hope so. And now it's my turn. I'm from the Constellation platform that's already existing right now. We want to turn this basis and do this into a sensor grid. And we are a student group. We are a DGLR, that's the German Aerospace Society group, a young academics group, and we do applied sciences and use-oriented aerospace research right now. And it's a really interdisciplinary collaboration. Like I said before, DGLR, Rechenkraft.net, SafeNet, some of them are already here, and of course Checkspace. So it's really, really interesting. And what we're basically doing is this, but that's not our machine. That's the HLRS, that's a supercomputer also based in Stuttgart. They are on the 12th place in the top 500 ranking. They have about 800 teraflops, but they cost 30 millions. And we are this small. Because we are relying on your computers, I will tell you afterwards. We have 2 teraflops right now, that's so in this range, but we only cost 300 euros, so it's rather cheap in this position. So and how do we do it? We do distributed computing with Boink. I think everybody knows this. So you guys are donating idle PC time to science, in this case to our system, and we have about 2,000 users and 5,000 hosts PCs. And if we only can make 10% of them plugging in the antenna these guys are building, then we have a huge basis already distributed in about 66 countries all over the world. And currently they have nothing to do, just spending some idle time for a so-called SN trajectory optimizer for a high-end student group at our university, and I'm doing the thrust optimization of them for the hybrid rocket system. So we could possibly and hopefully turn some of them and plugging in the antennas, so we also already get some distributed computing system as a basis of this. And we want to have the sensor data processed also on our system, and we also want to make these data available in raw form. So you can already start doing some good things for science currently right now. So this is nothing new. This has already been done. The Quakecatcher network is already doing this with some accelerometers built in some Macs, or with a small USB device you can plug in anywhere. And that's my favorite. It's called Radioactive at Home. You can measure radioactive background stuff at your home. So that's nothing new. You have this as another application. So going back to you, and we need some more help with volunteers. That are you, amateur radio experts, and of course institutes like universities and other important persons. And we want to have antenna modes with fixed single antennas. That's the basic stuff everybody can participate in. Fixed triple directional antennas, that will be more costly because there are 3 of them, but they give us more possibilities afterwards. And of course, motorized single directional antennas with high gain antennas like satellite dishes, that will be done by the institutes because they're really big and expensive. And with this kind of hybrid antenna mode, we expect that the accuracy will be much better afterwards. And the expected sensor grid we want to have is at least 1,000, but over 9,000 would be very, very appreciated. Okay. We are also thinking about doing some more mathematics. So there's this so-called one-way ranging, sending something from Earth to the satellite and back. But we are not in the sending mode right now, but we are already thinking about it. So so-called one-way Doppler system from the French guys using this for Doris. Multi-way ranging, that is what we expect with a distributed sensor system as well. And we have some contact with Dr. Sakamoto from Tohoku University in Japan, who does some crazy stuff and good things with Doppler shift experiments. I'm not really knowing anything about because I don't understand it, but it's working because he's doing it right now. And when you have some ideas how we could do it, give me an email, please. So why do we do it? For science, of course. And for other reasons, like I presented before. Okay, now to give you some impression where we are placed, because you can say, perhaps there is a system currently doing this. Yes, of course, you can do it with inertial measurement systems, and I think some of you already do, and with UAVs and so on. And of course, a space-based satellite navigation system like GPS or GLONASS. The GPS is operated by the US Department of Defense, and GLONASS is now controlled by the Roscosmos, the space agency of Russia. And they have something in common. When your satellite gets lost, because everything is stored on the satellite, you don't get any data back. So it's nothing worse when you know where you are, when you're not sending it to the satellite owner afterwards. So we want to have it externally, and the governmental agencies already doing this with NOAA and United States Strategic Command. They're tracking everything with radars that's greater than 2 centimeters, like a coin, or the European Space Tracking S-Track, and the so-called DORIS of the CNES, like I mentioned before. So they have different objectives, different functions, and they are under different management. And the distributed ground station network could become a new player in between them with a decentralized responsibilities. So what else can we do afterwards when we really achieving our goals? There are some crazy papers in the internet I really love, like atmospheric measurements or just measuring the accuracy of the GPS itself, because that's also important, because you want to know when something is going blurry on your radar. Then environmental monitoring by wireless communication networks, that they proved that you can already do measurements in the atmosphere with UMTS and GPS. So it's basically the same. We have to just figure out how the frequency is playing in this. Perhaps thunderstorm, strikes and cell detection, or that's my favorite, nuclear detonation detection. I'm not sure how that works, but I found a paper explaining this, and I would really love to detect one. So not because the detection, but I want to prove somebody is playing around in their foregarden. Okay. We talked about the antenna system. We also need a beacon. That's a concept, nothing more. We want to transmit something. We need a protocol for it. We have to establish a data rate. What we need for the complete cycle, and of course for the use data, that's important. And the ham radio community know OSCAR, that's the orbital satellite carrying amateur radio. I would also like to have an own ID for our purposes. And in this case, there's another interdisciplinary partner, the Aerospace Lab in Stuttgart-Herrenberg. They are high school students, and we want to have them build and helping us with the beacon itself. And the beacon itself should be as simple as possible to have more possibilities with it, because I will come to this later. And now you could ask us, okay, do you really think you can do this? Yes, of course. There's a Fun Cube, that's a small satellite lying on the floor there. It's built in the United Kingdom, and they have something called the Fun Cube dongle. It's such small, and they already can receive signals from space, so with some data rates in it. So it's very, very possible to do this. And now for the future perspective, besides the time measuring, the first thing I would love to have is tracking satellites, of course, tracking aircrafts, that's currently being done. Then helping science experiments or weather balloon, that's a Rexus and Bexus campaign, that's a rocket and balloon experiment for university students. You can apply for it for a small slot and put your experiment on board both, and perhaps that's a really nice test bed for us later on, for our beacon and also tracking them. UAVs, these guys, the UAV NG are currently doing some great job, some stairs up. And of course, for the Stuttgart Adler, that's also a plane, a small plane, and we also would like to help them as well. Of course, OpenStreetMap, because when you have a beacon that's really, really small, fitting into your pocket, you can do your walk around and then tracking where you have been, and then helping OpenStreetMap doing the material, the mapping stuff, and like mentioned before, the differential GPS, improving your GPS system, and of course, animal tracking. Future perspective and chances beyond the system. So our platform constellation could be the first application for the distributed ground station network, but it's not exclusively done for us, because spin-offs and derivatives should be done for everybody. And like I said before, I would love to have some small devices, and in this case, the so-called fast deployable antenna, WOF antenna, you can just implement here and then tracking the UAVs upstairs. Okay, and we want to have it with you, by you, and for everyone, of course. What I've learned so far is interdisciplinary collaboration works very well with hackers, science, and volunteers, and I'm really grateful for this. Almost everything is already available. We just have to bring it together in a sensible way. We have to keep on working because it's hard, but it's really doable. So your communities are really great because you have a lot of support for the Constellation platform from the Czech space and possibly for you. And of course, space rocks. So I'm done. So now it's time for some wide questioning, and thank you for your time.
Thank you so much. We do have time for a few questions. Please put your hand up if you have any. We have a question from the IRC right away. I'll get down to you.
Okay, Datenwolf is asking why you rely on governmentally controlled clock sources. He thinks that high precision clocks are affordable and rubidium frequency clocks normally go for about $150.
Yes, why are we relying on this? It's simple. We had it lying around, and it works really, really well because GPS is meant to be a time distribution network. We also could use a module using a similar interface that is based on GLONASS or Galileo or the Chinese variant, and it is very unlikely, at least in the beginning, that all these governments would turn off something at the same time. So we just used that to get started. Hope that answers the question.
In the back?
Yeah. I have to thank you guys, because with your work on timing, you might have done about half of my diploma thesis, which I started right now.
You're welcome.
Seriously. We are working on a network of close by but distributed nodes of detector for cosmic ray incident light. So we are looking for Cherenkov light coming in from proton collisions in the upper atmosphere. And the easiest way to get good precision is to get a bunch of detector stations which you place at a couple meters or a couple 100 meters from each other in a huge area. The system that we are hoping to deploy, we're going to be testing in some part of southern Siberia. And actually for the timing that we've been thinking about, nothing much has worked out yet, which is why it's perfect that I got to see this talk. We were thinking about a two-stage timing system where you would have 1 PPS or maybe 100 PPS level accuracy from GPS or satellite systems, and then a second level system that gets us down to hopefully 1 nanosecond, which is what we need for evaluating our signals. And I think the system that you described with the Arduino board, which is perfect because we've been struggling with closed hardware, could serve as a first level module or even the timing module of some maybe not so time critical science applications. So I'd really love to get in touch with you because you could do stuff that helps astrophysics a lot, because these distributed cheap detector stations which you distribute over a large area is probably where astroparticle physics is going to go by large parts. So yeah, great. Here we are.
That is good to hear, that people actually are needing this, and it's not just us having brain farts. So feel free, by all means, to come upstairs to our desk. You cannot miss it if you look for the big posters, and we'll have a talk. Any more questions?
Yes, we do have more questions from the IRC. That's 28C3 SAR2 in this case on Freenode.
So Fidepus asks what he has to do to become a dot in the grid. He wants to build hardware.
That is good. That is a good question. Talk to us probably would be a good start. He can sign up for this mailing list here. It's public. Just sign up there, ask us questions, or come up to us here at the Congress and we'll talk about the details. Everyone is very welcome to join. There's too much work for just us to do.
We have another question from the audience up front.
Yes, this reverse constellation and positioning you were talking about, at least for positioning, right? So that means it's at least a bidirectional communication between all the ground station and this one flying notebook, right? What's the frequency band and the output, the field strength intended to have?
Okay, the reverse GPS is just an example to present you how it's done. But every antenna these guys are building have to have a small device that's really measuring your position, or you have to put it in because you know the time when the signal is going to the antenna from our beacon and the position of each and every antenna. And then you can calculate it. No. We just have to receive it from somewhere. So manually putting in, that's something really very difficult for some persons. But when we put in a GPS or whatever, like donut system and so on, it's also already also measuring the position itself. So we don't have to be bidirectional because then it's sending and we don't have the license for this yet.
So we're talking about just receiving?
Just receiving and listening to whatever's going to the antenna.
Yes, at this point, we don't have any intentions of violating any laws by sending stuff. That is maybe coming in the future. Who knows?
Okay, another question from the audience at the back.
You mentioned that you looked at NTP for time synchronization and rejected it as too imprecise. Did you look at alternative protocols in that area? I remember vaguely seeing papers and about other approaches of the same kind, though.
One thing that was very important to us was that the ground station should be independent, at least independent for a while from an internet connection. Like you could just take it somewhere with you where you don't have any internet connection or the internet connection is unreliable, and it saves data and timing information and any stuff, and then it sends it, when it gets to the internet again, it sends it back on the BOINC network, and the information is then processed. So since we need to keep the clocks constantly in sync, it would be bad to be dependent from the internet or any other network.
And to add to this, the described Axis and Axis campaign, they are starting from the northernmost part of Sweden, and there is no internet. And I would like to have this small deployable antennas there when we are doing this, and hopefully doing this. And we would to have it modular, so then you have GPS module you can stick in, or some other sources, and it just depends on your application you want to do with it.
Yes, it's a little bit of a chicken-egg problem, because we want to get rid of the cable-bound internet, and if we depend on internet for our most basic thing, the timing, that is kind of a problem. Does this answer your question?
Okay, it does. We do have another question from the IRC.
Bibor wants to know if you ever heard of MSAT. It's, I think, an organization who are working, who's working in high infrastructure and know-how for satellite communication, and if you have ever thought of working with them.
Yes, of course, we have heard of them. The FunCube is also somehow related to it, and first of all, we want to have it working. So we're already talking to some people, and we would love to talk to them as well, but we want to have at least some achievement. So give us some time, please.
Yeah, we just started hacking and then started talking to people. Now it's working at the same time, but yeah, as time goes by, we get more and more contacts. If you want to put us towards any group that is already doing this, please do feel free to send us an email.
Yes.
And write another question.
Okay, I have two small questions. ZZO wants to know how, or if you know about the time stabilization on the satellite and how this is done. I don't know. And Philippus added to his previous question if you are developing a model layout for a ground station, or if you're planning to do so.
We don't know yet about the time stabilization on set, but well, we don't have satellites yet, so that wasn't a question that we ask ourselves. And we are do you have any?
But when this person is knowing this, he can help us. So.
Yes, if anybody knows this, well, do share. The second question was, are we, what?
If you're planning on doing a model layout for the ground station, or yeah.
Yes, this is the basic idea, that we want to build some very, very simple interfaced modules for timing, for getting the position of the ground station, and for plugging in any possible kind of measurement system that you want to use, be it satellite or your weather station, and go from there.
Okay, I see we do not have any more questions. If you do not want to ask a question in public, just come after the talk. Thanks again.
Thank you.